In this lecture, we're going to talk about what determines the cell size and how we can model this mathematically. So this is going to be our very first real application of our mathematics to real biological processes, but we're going to use everything we've built up so far, including power functions and their relationship between each other. The question really is, what physical and biological constraints determine the size of a cell? Why should most organisms on Earth be made up of millions and millions of tiny little cells as opposed to just a few big ones? Why do size limitations even exist? And maybe the nature was doing it all wrong. I highly doubt that because the nature is pretty sophisticated, but we're going to figure out what mathematical principles underlie such natural decisions. First of all, we're going to start off by making a few assumptions. We're going to start with the simplest but quite common cell shape, and that is a sphere. We already saw an example on spherical cells in terms of the dangers of getting wet. Here, we're going to think about what it means in terms of their actual size. We're going to make the assumptions that the cell absorbs nutrients through the surface, so as it comes in contact with them from the outside, and it's going to absorb the nutrients proportionally to its volume because it does have to sustain life within its entirety. The larger the surface area of the cell, the more nutrients it can absorb through the surface area. But on the other hand, the larger the volume, the more nutrients it actually needs to be able to survive. And that is, in fact, the balance that we're looking for. What is the relationship between the absorption and the consumption? The one characteristical descriptor of a sphere is, of course, its radius r here. So that's the one we're going to be working with. We're going to fix some radius of the cell. We're going to say that S is the cell's surface area. And we've seen formulas before. The surface area of a sphere is 4 pi r squared. V is going to be its volume, which is 4/3 pi r cubed. We're going to have two letters to denote absorption and consumption rate per unit time. In order for the cell to live, it of course has to eat more than it has to consume. So in order for the cell to survive and thrive, the absorption of nutrients has to be greater or equal than the consumption of nutrients so that we have some reserve food in order to consume it. Now let's think about what our assumptions were. The cell is spherical, which means that we have the radius, we have the surface area, we have the volume formulas as on the previous slide. And then we decided that a reasonable thing to assume is that the rate at which the nutrients are absorbed is proportional to the surface area. So it absorbs nutrients through the surface area. Absorption is proportional, using our proportionality notation, to the surface area. So the absorption is proportional to 4 pi r squared. Because we're going to be working with balancing and therefore want to see equations, we should turn this proportionality relationship into an actual equation. So remember that proportionality means that the first quantity is a multiple with some kind of proportionality constant of the second one. So this proportionality constant K1 is going to be greater than 0. On the other hand, we also assume that the nutrients are consumed at a rate proportional to the volume. So the consumption is proportional to the volume, which means that the consumption is proportional to the 4/3 pi r cubed. And again, turning this into equation means that the consumption is equal to some kind of proportionality constant times the actual volume formula for this constant K2 that is positive. Fantastic. So we decided that for the cell to survive, we need that the absorption is greater or equal than consumption. And now we have both of the formulas present in terms of various constants, proportionality constants, pi constants, and more importantly, the radius of the cell. So let's see what we can do about determining when this is actually going to be the case. So again, what we want is the absorption greater or equal than consumption. From the previous slide, the absorption is K1 times 4 pi r squared, and we want this to be greater or equal than consumption, which from the previous slide is 4/3 pi r cubed. So let's see what we're working with here. As I already said, K1 and K2 are proportionality constant. 4 is a constant, 4/3 is a constant, pi is a constant here and there. So what I actually have, I can group these things together. K1, 4 pi is a constant that gets multiplied by r squared. So this portion of the absorption formula is actually a constant. And I want this to be greater or equal than K2 times 4/3 pi times r cubed, where what I have in the brackets now is also a constant. So I have some constant times r squared has to be greater or equal than some constant times r cubed. Okay, I know that it can be difficult to look past these large numbers, so squint at them, or let's rewrite them as some number times r squared has to be greater or equal than some number times r cubed, where the left-hand side here corresponds to absorption, and the right-hand side here corresponds to consumption. Now, this is really great news because r squared and r cubed are just power functions. So what this comes down to is simply comparing the two power functions, and we already know how to do that quite well. So for just a little bit of a graphical support, let's sketch a picture. So what we're going to have is, we're going to have a common graph for absorption and consumption. Now, notice that r here, our variable, is of course radius. So really, I'm only interested in this graph for positive values of r in here, because radius of a cell cannot be negative, but I'm going to include the other two quadrants just for the sake of when I'm sketching the graphs, making sure that I'm sketching the appropriate graph and seeing what it does look like mathematically on the biologically irrelevant side. So my absorption is r squared, which means that my absorption is a parabola. R squared times some number, I have myself a parabola. This corresponds to some number r squared, or let's label it absorption. Fantastic. Now, the consumption here is some number times r cubed, which means that it's a cubic function. And now I have to draw it on the same graph as my current quadratic function. So what am I going to have? Remember that according to the power dominating analysis, a cube being the higher power than the square will lie below it near the origin, and then eventually will switch out and start increasing faster and faster. So I have the snaky shape in the negative. It's going to be below at the beginning, and then will eventually switch over and start growing faster on the end here. So this is my r cubed that corresponds to consumption. Okay, so what does that actually mean? First of all, we can see that this switch point, of course, is now quite important because something happens at the switch point. What we see is before the switch point, the absorption, my purple graph, is on top. So the absorption is higher than consumption. But after the switch point, the consumption is higher than absorption, which means that the situation reverses completely. So I'm going to split my regions of consideration of the sizes of R into two. On the left-hand side here, so between 0 and this switch point value, I can see that the absorption is above consumption. So let's record that. Absorption is above consumption. And after the switch point, consumption is on top of absorption. So consumption is bigger. So what are we looking at here? When the absorption is higher, that means that the amount of nutrients a cell absorbs is bigger than the amount of nutrients it consumes, which means that the cell will in fact survive. Afterwards here, if the consumption is bigger, it means that the cell needs more nutrients that it is able to absorb, and therefore it will eventually starve. So this is a critical value. Before it, the cell will survive and thrive, and after it, it will starve off and die. This is why spherical cells are small, because they will only be able to absorb enough nutrients for their consumption for some radius size between 0 and this critical number right here. If they grow bigger than this number, they will simply not be able to absorb as many nutrients as they need. So let's take a look at a few examples of the actual cells and their sizes. So here is a scale. We start off with atom, teeny tiny, and grow sort of bigger and bigger and bigger. And we notice that cells, of course, are not generally very perfectly spherical, but we can pretend that we can abstract far enough from that. The viruses are actually fairly well rounded, as well as, for example, red blood cells. The animal cells and the plant cells that tend to be on the bigger part of the spectrum have much more complicated structures and cannot be simply assumed to be very, very trivial spheres with nothing in between, right? So the smaller cells tend to be much more spherical and uniform in nature, whereas the larger ones tend to be much more complex. Now, it is important to notice that there's a few quite drastic exceptions to the analysis that we have just performed. In particular, neurons are huge cells. They extend out and occupy actually quite a bit of area in terms of cell size. Huge for cells, not just huge in general, right? But the thing here is, our analysis, we assumed that the cells were spherical, which neurons, of course, are not. Another notable example of an exception are very flat filament-like sheets that are one-cell organisms in this type of sea plants. And then, of course, again, our analysis doesn't actually apply because these cells are far from spherical. So it's not that our analysis fails or is wrong, it simply isn't applicable to these cells. And in order to analyze what the size of these types of cells will have to be, we will have to consider their shape and come up with the absorption and consumption formulas for their particular type. The other exceptions are various plant and animal cells that do not necessarily absorb all the nutrients from the outside, but rather actually store water or other various nutrients inside of them, which doesn't work with another assumption that we made, and therefore our analysis will not apply to the cells of that size. Same with things like eggs. These are quite large cells, but that is because they keep the nutrients that they need on the inside of them, only absorbing really oxygen from the actual outside. The conclusions are, based on our assumptions, if you are a cell and you want to be big, there are a couple of things to do. First of all, don't be three-dimensional, be flat, like a filament or a sheet in terms of the various sea plants that we're used to seeing. The other thing is, of course, not consuming proportional to the volume, so maybe consuming in a bit more of a economical manner. The other thing that it does not say here is maybe don't absorb proportional to the surface area, much like the plant cells that keep some of their nutrients on the inside. The other thing is we can actually play around with the constants a little bit. If you remember the graph that we sketched, we had a quadratic function and then a cubic function. If K1 is much, much bigger, which is what this means, than K2, then this point that corresponds to the critical cell size will actually be quite far into the sort of radius size here. So this point will actually be quite big. And therefore, we will be able to have a bigger cell here. And the one thing that this corresponds to in nature is to have highly permeable shells, so be able to absorb nutrients and also from the outside a little bit more effectively. And of course, we can store everything we need on the inside, which will correspond to the absorption being a little bit skewed off and our assumption on that not quite holding. This is a very important point that I will emphasize over and over again. Predictions of any model that we are going to come up with are only ever going to be as good as our assumptions. If our assumptions do not hold for a particular cell shape or absorption way mechanism or anything like that, then our conclusions also cannot be applied to those cells. Okay? If you've assumed something not that you're currently working with, then the conclusions will also not apply. The other fun rule that is a bit of a urban myth, but seems to be supported well by observation, is so-called Bergmann's rule. And the idea here is that because larger animals have lower surface area to volume ratio than smaller animals, they radiate less body heat per unit time. So they let go of less body heat, which means that small animals have the exact opposite, lower surface area to volume ratio, so their body heat is dissipated quite quickly rather than stored within the body. And the natural conclusion to draw here, if you wish, is the fact that species of larger sizes that are able to hang on to their body heat more effectively are found in colder climates, as opposed to smaller sizes animals that are found in warmer regions. And of course, because there are similar animals in different parts of the planet, we can actually collect examples of whether or not this is supported by observation. So, for example, bears, polar bears versus brown bears. The sheer difference in size seems to support the Bergmann's rule or principle. Polar bears tend to be a lot bigger than brown bears for supposedly the reason that they, being creatures that live in colder climates, need to radiate heat less than their brown bear relatives. Hares versus rabbits. An Arctic hare is much bigger animal than a rabbit that we actually see, I often see right outside of my office at U of V. Of course, we have snow people. Canadian snow people are much bigger than Brazilian snow people, and so on and so forth. It is important to remember that whenever you're reading about rules or laws, such as the Bergmann's rule, that if they are not supported by specific calculations and the showing of the fact that the principle is based on some kind of underlying laws, then they are simply a bit of a myth. While there are examples throughout the world that support this rule by observation, it is by no means an actual physical or natural law that holds throughout. In the first part of the lecture, we considered spherical cells and their consumption and absorption. Here, we're going to consider cubic cells. And in particular, we're going to consider cubic cells so that they only absorb nutrients through the top surface. So if they're positioned this way, right next to each other, the absorption of nutrients only happens on the available surface that happens to be the top because the sides are adjacent to other cells around them. The consumption happens to be proportional to the volume of the entire cell because it does have to sustain life throughout the whole volume of what it occupies. We're first of all asked to find the absorption rate and the consumption rate of this cell. So in case of a sphere, of the spherical cell, we had that the characteristic of it that we relied on was the radius that uniquely determined how big the cell is. If we're talking about a cube here, then the measurement we're looking for is the side length, which for cube will be the same in terms of length, width, and height. So first of all, let's talk about absorption. Again, it's proportional to the top surface of the actual cube cell. So if it's x in each dimension, then the top surface has the area x squared, because it is in fact a square, right? X times x, length times width, which means that the absorption is proportional to x squared. The consumption, though, is proportional to the entire volume of the cell, which is length times width times height, which is x times x times x, or altogether x cubed. So in fact, while we traded the radius for the side length, we actually see a very similar relationship of the absorption being proportional to the square of the characteristic measurement of the cell, and the consumption being proportional to the cube of it. Now, as before, in part 2 of the question, we will sketch both of the rates on the same graph and then look at it to see how the graphs actually interact with each other to determine whether or not smaller or larger cells will survive in terms of absorption or consumption rate being greater or smaller. So from the previous slide, let's recall that the absorption is proportional to x squared and the consumption is proportional to x cubed. So if I draw my graph, I need to draw the x squared and the x cubed. And remember that because x represents the side length of a cell, x's that we are going to care about are going to be positive. I'm going to draw the graph for both negative and positive direction to sort of be mathematically comprehensive, but we only really care about what happens for positive values of x. So absorption is quadratic, which means that absorption is going to have a parabola shape of x squared shape, being, I'm trying to be as symmetric here as possible. So this is my absorption. Now, next up is consumption, which is a cube. Remember that near the origin, the smaller power dominates, which means that the larger power, the cube, has to be below the smaller power, absorption being the square. But then eventually it will switch over and beat the smaller power in the long run. Now, x cubed is also snake shape. So we're going to start down here. At the beginning, it's going to be below, and then it's going to cross over, switch over, and be above. So we notice that there's actually 2 points of intersection at the origin and at the switch point. So what happens here is we notice that for small values of x, which is the side length of the cell from the previous slide, for small values of x, we notice that this graph, which is absorption, is dominating, which means that absorption will be greater than consumption, and therefore the cell will be able to take in more nutrients that it uses, and therefore it will in fact survive. So here, absorption is greater than consumption. Whereas past the switch point and from then on, we notice that the consumption is dominating. So the cell will consume more nutrients that it is able to absorb, which of course means that it will eventually starve and therefore not survive. So here, absorption is less than consumption and the cell is not in good shape for long-term survival. So to sum up, we're going to say that near the origin, first of all, the graph of x squared dominates, which means that the absorption actually dominates, which of course in turn means that the cell is able to survive. So small cells are able to absorb more nutrients and therefore live. Small cells, and in particular for small values of x, because x characterizes the size of the cell in this case, are able to consume more nutrients that they need to survive, and so they will live. Whereas after the switch point, the consumption is going to be bigger than absorption, so the cells will not be able to obtain as many nutrients as they need for survival. So in this case too, small cells are in the advantage. Let's take a look at yet another different shape of a cell, cylindrical cells. So we're going to consider a cell in the shape of a thin cylinder of length L and radius R. So notice that here, for the first time, we actually have two characteristic measurements. In terms of a sphere, we only had one, which was radius. In terms of a cube, we only had one, which was the length of the side. When it comes to a cylinder, we need to know both its length and its radius. We are going to assume, in a similar fashion as before, that the cell absorbs nutrients through the surface, which does not include the end caps of the cylinder, and consume nutrients corresponding or proportional to its volume. And once again, the problem is the same. We're going to find the absorption and the consumption rate and then try to analyze whether small or large cells have an advantage in terms of survival. So first of all, let's just do a rough sketch of what a cylindrical shell might look like. So cylindrical shells are a specific technique in Math 112 or Math 118, which is why I keep saying cylindrical shells. Cylindrical cells in this particular course. So this is my cylinder or cylindrical cell. I'm going to have a radius, which corresponds to how sort of wide the cell is, and I'm going to have the length, which corresponds to how long my cylinder is. Now, if I am to talk about the surface and the volume of this particular cell, it means that I need to know what the surface and the volume of a cylinder is. So just in terms of the cylinder itself, the surface area of such a cylinder that does not include the end caps, so I'm not thinking about the caps, I'm only thinking about the actual lateral surface area here, it's equal to 2 pi r times L, whereas the volume is equal to pi r squared L. Okay, so now what do we have? We have that the absorption is proportional to the surface area because this cell is assumed to actually absorb nutrients through the surface area. Absorption is proportional to surface area, again, not including end caps. If we were to include end caps, we would have to add pi r squared twice for the two circles on the ends of the cylinder to this particular expression, but we're not actually interested in that now. So absorption is equal to, it's proportional, so some kind of proportionality constant times the surface area, which is 2 pi RL. 2 pi RL. The consumption, we're told, is proportional to the volume. So in terms of the equation, we have that the consumption is equal to some kind of constant, proportionality constant, times the volume of our cylinder, which is pi r squared times L. Excellent. Once we have this, we can move on and analyze the cell survival rate or behavior in terms of consumption and the absorption. So first part is to figure out when are they exactly the same. So where is that switch point at which the consumption is going to be equal to the absorption? So first of all, let's write that down. So I would like the consumption to equal to the absorption. And so from the previous slide, I have that the consumption is proportional to the volume, so K2 times pi r squared L, and the absorption is proportional to the surface area, which is proportionality constant K1 times 2 pi r L. So let's take a look at this equation here. What are the types of things that we can do? First of all, we can of course notice that there's L present on each side, and we can try to divide by L. But as before, I strongly recommend against dividing and rather advocate for factoring. You could make a case here that you could in fact divide both sides by L, because L being the length of your cylinder cannot be 0. But then you have to specifically say that that is the case. So instead of dividing and making an exclusion, I recommend we move these things over to one side and then factor as much commonalities as possible. So K2 times pi r squared L minus K1 times 2 pi RL is equal to 0. And now that we have everything on the same side, let's see what it is that we have in common. We can factor out the pi. We can factor out one of the r's, because this factor has 2 and this factor has 1. And we can factor out the L. So altogether, we can factor out pi RL. What are we going to have left? From the first term, we're going to have K2R. And from the second term, we're going to have 2K1 left. So all of that is equal to 0. So once again, the strength, the real force behind factoring is the fact that now I have myself a product of 1, 2, 3, 4 things that is equal to 0. If a product is ever zero, it means that one of the multiples that compose that product is itself a zero. So what that means here is either pi is zero, which of course is impossible. Pi, we know, is a number that is not zero, or r is zero, or L is zero, or this bracket is zero. So K2R minus 2K1 is equal to zero. Notice that I can immediately eliminate these two cases as not being biologically relevant. And that, of course, is because these would represent the case where the cell is trivial, non-existent. Either the radius is zero, so my cylinder doesn't have a radius at all, or the length of it is zero, so it's simply just a point. So these are not biologically relevant. They are, of course, mathematically present, but not biologically relevant to our situation. On the other hand, this other case is something that we need to explore a little bit further. K1 and K2 are proportionality constants, which means that they're numbers. So the only thing I can solve for here is R. And if I move things around, I can see that R is going to be equal to 2K1 divided by K2. So I have myself an actual number that R, the radius of the cell, can be, such that consumption is exactly equal to the absorption. Now, in order to get a real handle on this, let's actually sketch what we have so far. Now, we've already decided that our radius and our length have to be positive in terms of, in order to be biologically relevant. So I am going to really only concentrate on what's happening in the first quadrant of this graph that I am drawing in terms of R. So in terms of R, my consumption is proportional to the R squared. So it's proportional, with all other things being held constant, to the quadratic, or in terms of the graph, a parabola. So here is a parabola that will represent my consumption. So let's label that. On the other hand, in terms of my absorption, all other things being held constant, it's proportional to simply R, which of course is a linear function, right? Think about y equals x or something like that. It's proportional to a line, and so now we have to figure where the line fits, in which way, right? It is a power of 1, so near the origin, it will dominate the power of 2, that is consumption here, but then at some point it's going to switch over and fall below the quadratic. So this will represent my absorption. So now what I have, of course, is even from the graph, I noticed that they intersect at 0, which was my not biologically relevant case of radius being 0, and they intersect again at some switch point, which is then given to us by this equation. So here I have 2 points of intersection, r equals 0, and then again, r being equal to this constant that I have calculated, 2k1 over k2. Now let's look at what happens before and after the switch point. So before the switch point in this region here, I have that the absorption is on top, so dominating the consumption. So the cell absorbs more nutrients than it consumes, which means that the cell will once again survive. Absorption is bigger than consumption, which means survival. Afterwards, from then on, I have that the consumption is bigger than absorption, so the cell needs to consume more nutrients than it can possibly absorb, so that means that the cell will in fact starve, in the case of consumption being bigger than absorption. So once again, similar scenario, small cells for the win in terms of cylinders. Again, it's not always going to be the case. We can think of neurons and we can think of filaments, but for the shapes that we've considered so far, which have been sphere, cube, and cylinder, it seems that the small cells, if they are sort of in terms of density and other qualities, simply the shapes that we are assuming them to be, the small cells will survive, whereas the large cells will struggle. Now let's take a look at a particular kind of spherical / cylindrical type of product, and these are going to be gourds. In 1936, a researcher synod showed that there is a power relation, which we sometimes call allometric, between the length of a gourd, which is things like pumpkin and squash, and the width of it. So in particular, he showed that for pumpkins, that relationship is portrayed by the exponent of 0.95. And for the snake gourd, something like this, the relationship is portrayed with a power of 2.2. Whereas to plot this relationship on the same axes and then figure out what the proportionality constants are, given that we know that they both go through this particular point of 10 for the length and 10 for the width. So first of all, before we actually sketch anything, let's just think about what does that say in terms of pumpkin and in terms of snake gourd for the formulas. So what we have is we know that there is a proportionality relationship between the length and the width. Okay, so the length is equal to some kind of proportionality constant times the width, and we're told that the width isn't just itself, rather the exponent is 0.95 for pumpkins, and the exponent is 2.2 for the snake gourd. Notice that my proportionality constants have to be different. So in this case, I call them K and C. Pick your favorite two letters of English or any other alphabet, and you're good to go. So the exponents are represented by the powers of the width here. The next thing we know is that they both go through the point 10, 10. So that means that I can plug 10 in for the length and 10 in for the width and solve my equation for the proportionality constant in each one of these cases. I recommend you pause the video and go through the actual algebra yourself to figure out what K and what C values actually are. Okay, so if I plug in 10, that will leave me with only one unknown, which is K. And rounding down to two places, I get that in this case, K is equal to 1.12. So that means that for pumpkins, I have that L is equal to 1.12 times W to power 0.95. Going through the exact same kind of procedure for the snake gourd, I will have that C, the proportionality constant, is equal to 0.06. Again, rounding up to the two actual decimal places, and that will give me the formula L is equal to 0.06 times W to power 2.2. So now we can actually go ahead and sketch these two relationships to see what they look like. Now, of course, you can do this by hand, but why do that by hand when we have ourselves desmos? So these are my two formulas that I've derived with proportionality constants that I see. And this, on the right-hand side, is the relationship between them. Notice that if I actually zoom in, I will notice that this point of intersection isn't exactly 10-10. And that, of course, is due to the fact that I've rounded my proportionality constants to two decimal places. So my point of intersection will also be a rounded result. But if you zoom out far enough, at least the general qualitative shape of the graph tells me something quite useful. Let's extract this graph into our lecture notes here so we can annotate it and think about what actually happens. So here is my graph. I can annotate that this point here is 10-10 or approximately 10-10 due to my rounding. And now let's also actually annotate which of these graphs corresponds pumpkin and which snake gourd. So notice that the component for the pumpkin was 0.95. So even if I didn't actually have the particular entry for the decimals that I've myself put there, I would know that this exponent is close to 1, which means that this will be close to linear. 0.95 is close to 1, so this represents my pumpkin. So this black line is my pumpkin, whereas 2.2 is much closer to 2, which means that this will be a more parabolic shape. So this will correspond to snake gourd. So what we notice too is that in the interactions between themselves, for small values of the width, we see that the pumpkin will grow to be longer than the snake gourd, whereas afterwards the situation gets flipped and the smaller power will fall below the larger power and the snake gourd will dominate in terms of the actual length. Okay? Notice once again that the power analysis will never fail you. The smaller power dominates near the origin and falls below for large values of x, whereas the larger power is smaller near the origin but ends up dominating for large values of x. Power analysis always works as a great common sense check in all kinds of situations.